Okay, class, I'm here to talk to you about a fun story. The story goes like this. There was a mathematician. He was studying math in London, and he went to Oxford, and he studied math there until the turn of the 20th century. And he was undergoing a lot of influence by the newest thing at the time, which was the development of statistics. And so his sort of field of math was really dabbling in statistics a lot. And so there was still a lot of discoveries to be made. He was employed, however, by not a college where he could do research in statistics and mathematics, but by the world's most famous brewing company at the time, Guinness Brewing in Dublin, Ireland. And he shipped off out of country into Ireland with he and his wife and family, and they went out there, and he became eventually the head brewmaster of Guinness Brewing Company, which is an amazing feat for a mathematician. Well, he was a chemist as well. Gossett had some issues because, see, previously at Guinness, some of the research scientists had published sort of their trade secrets and let people kind of know what they were doing. And so Gossett knew that he couldn't publish under his own name, and so he never did. He didn't publish under the name William Gossett, but we know it was Gossett who did what I'm about to tell you. He, through trial and error methods, figured out ways to produce barley, and hops for brewing beer in ways that nobody had ever done before. And the methods that he utilized was an experimental method with small sample size. And this became revolutionary. It became so revolutionary that it allowed you to do what you're doing now. It allowed you to have the use of science at any moment. It allowed you to be thinking the way you're thinking. The things that I've said that are taken for granted now, that we can use a small sample and then that projects to the population from which that sample was drawn, is fundamentally about William Gossett. Dr. Gossett changed the way that we consider how samples could be used to estimate that of populations. Now, Gossett was a very humble man, unlike his contemporaries and his friends and mentors, both Carl Persson and Sir Ronald Fisher. Gossett was a humble and kind person who befriended both of these juggernauts of statistics, Persson and Sir Ronald Fisher. And Persson kind of took him under his wing and helped him. And Carl Persson's the guy who developed the idea of correlation and created correlation coefficients. We'll talk about him later in the class. And Sir Ronald Fisher is the man who discovered the ANOVA, and I will reveal to you his genius later in this class as well. These guys were Newtonian-level geniuses of math. But they didn't discover this. Gossett did. See, Gossett had a problem. He had to figure out, how do I figure... Let's consider an example. If you're brewing, and at the time they would ship out... let's say you have these giant vats of beer, and you're going to go into production with all this beer, and then you're going to send it out to, the Irish countryside, to some pub in sort of a Tolkien-esque little cubbyhole of a hillside tavern, maybe Chaucer-esque. You don't know if that beer is going to be bad or not. And the way they would ship it out, sometimes the pubs would say, oh, that was a bad batch of beer and we're not going to pay for it. Now, they didn't know whether or not it was, and they didn't know how to take a small sample and then to project to the population. So statistically, Gossett figured out how you can take a small sample of something and then use what's called a t-distribution. And that t-distribution takes into account the small sample projecting to the population from which it was drawn is going to have a little bit of error. And so it doesn't follow the same normal curve that we've been doing with the z-test. He had to develop a new distribution. It's called a t-test. And basically, the idea is that the larger the n size you get, the less error you'll make in projecting what the population's parameters are like. So the small sample is it could be variable. If you remember our example of one person and we said that, she wasn't given any participation awards, and the chance of her coming from anywhere in that comparison population was very high because it was just an individual. But as you increase the sample size, the chance that the mean of that group, the larger sample size group, does not reflect that of the population diminishes exponentially. As such, Gossett discovered this and realized that this could be utilized in small sample sizes to project to population means. And if we could estimate parameters via small samples, literally the world of science opened up. I don't know how William Gossett is not a name that every single school's child is taught in the history of science. You guys hear about Darwin and you hear about Newton. Well, without Gossett's insight, without his creation of what he called students' t-tests, and we'll get to that in a second, you would not be able to run experiments. You wouldn't be able to do the science that you'll be taught to do in your undergraduate career. Without William Gossett, the man who gets... He was really like shamefully shy and never wanted to aggrandize himself and published under a pseudonym. There were reasons that he did that, but again, it was a lot of personality as well. He didn't have the sort of braggadocious styles of Carl Pearson and Sir Ronald Fisher's sociopathic focus on himself. But he is extremely important. Without William Gossett, we don't have the iPhone you might be watching me on. We don't have the internet. We don't have supersonic jets. We don't have telecommunications and satellites, and we don't have modern science without William Gossett. And I've sort of made it my my crucible to make sure that everybody knows how important it was that he developed this single test that you're about to learn called Student's T-Test. It's not something that will be difficult for you, but it was radical at the time. No one had done this yet. And it's not like, with Darwin, he had Wallace, who was doing the same thing at the same time as Darwin, and a bunch of people had said what Darwin had said before. It's not like Newton discovered gravity. Other people had thought about this thing before. He articulated it well. He's the one who's given credit for it. He's the one who sort of paved the way for us to understand the force of gravity. Literally, Gossett discovered this. Although he was so humble, he said, if I hadn't discovered it, Sir Ronald Fisher would have. Don't give me credit, he said. It would have been Fisher. Now, he published under the name Student because Guinness had problems with trade secrets. And also he figured, if he published under the name Student, then it's going to be given credit to the people who can use it. Any proprietary branding of this particular method of statistical analysis will be given to the author, right? The author will retain ownership of it. I'm not sure if you're familiar with 19th century Irish tort law, but let's consider like today. If you go and you work for Google and you write some amazing code while you're at Google, they own the code. You don't get to profit from it. So frankly, I'm thankful that he published it as Student, not as Gossett, because as head brewer, he wasn't head brewer when he discovered this, but he was up there. As an employee of the Guinness Brewing Corporation, they would have owned the Student's T-Test, and you wouldn't be watching this on a Samsung or an Macintosh or a Vizio or an Acer laptop. You'd be watching this on a Guinness Brewing laptop, if there even was laptops. You'd be driving a Guinness car, if there even was the type of cars that we have. So his publishing this anonymously as a pseudonym of Student not only gave it to you and sort of made you in charge of what happens in science, it's a call to duty for you, that this enables you to do the work that would have taken people way too long. This speeds up the process. Maybe you guys have heard about CRISPR and the massive advances in genetic research that we've been able to unleash based on a new development called CRISPR. They'll win the Nobel Prize for sure. But Gossett didn't get the recognition that he deserves. And so I always like to tell everybody the story of Gossett and how wonderful it was, and that he actually gave you Student's T-Test. You're a student, he gave it to you. It's named after you, and you can use it now. So let's go figure out the mathematics of how do we use a sample to project to a population. Okay, class, we're back, and Henry left us with a man who's losing his marbles, barfing rainbows. I think my boys are getting a little stir crazy here. So we're talking about William Gossett and his t-tests. So he created t-tests to enable us to sample a small sample and then project to the big population. So what are we going to do with that? Let's consider what the application might be for this. For example, I like to use the example of, let's do cognitive behavioral therapy to help people with anxiety. Now, the typical treatment for anxiety is going to be an anti-anxiolytic. If you've taken any of my other courses, you know how much I'm against the use of psychiatric medications. But we want to compare the treatment, one treatment versus another. Now we know when you go into the doctor, you say, "Doc, I'm anxious. This whole virus lockdown thing's got me stressed." They're going to give you a treatment, and that treatment is an anti-anxiolytic. They're going to give you a drug, a Xanax or something that takes you down a notch and makes you not so worried about what's going on. So my example is going to be that we know people who get treated, the mu for people who get treated with the anti-anxiety drug, their average anxiety is 30. Can you guys see that? Let me see here. Okay, so their average anxiety is 30. This is just known from the psychiatric literature. We know about the population, and we know that their standard deviation is 4. Now, for us, we want to take a sample of people, and instead of giving them a psychiatric treatment like Xanax, we're going to give them cognitive behavioral therapy. So we're going to have a group of, say, 15 people. So N equal to 15. They come into the doctor and they're willing to participate in this study. So we're going to take that 15 people, and instead of giving them the treatment that they normally get, we're going to give them cognitive behavioral therapy. So they won't get the drug, they'll get the therapy. Now, the mean for them, the mean for the group of 15 people who did not get the drug, right? Our sample is going to be these 15 people. Their mean is actually 25. Now you might think, that doesn't seem like it's much different than the 30, right? Because maybe it's just that this group of 15 people, maybe they were less anxious than the average, right? Than the average person receiving treatment for anxiety. That could be it. So what we're going to do is utilize the t-test that Gossett developed, students t-test. That's where I'm comparing my sample to a known population mean and standard deviation, and we're going to use that known mean and standard deviation to project for us the likelihood that this sample would have been drawn from a population that has those parameters. Step number 1 of hypothesis testing, you guys remember, is to restate the question as a research hypothesis and a null hypothesis about the populations. So which two populations do we have? Population number... Can't see that. Man, I'm a terrible camera person. Let's see here. Alright, there's population number 1 up there. Population number 1 is this group of people, the group that had a mean of 30. They're the ones who get regular treatment. So, anxious people with drugs. Population number 2 is anxious people with cognitive behavioral therapy, CBT. Not CBD, not CBD, although potentially. It's better than the drugs you get. Okay, my null hypothesis, the HO, will be that there's no difference between these groups. That any difference we see is due to sampling error, just chance, right? That if you sampled once, you'll get this. If you sampled another time, you get another thing. So our HO is that population 1 is equal to population 2. Our HA, however, is that we believe that the cognitive behavioral therapy is going to do better, it will reduce anxiety. So population number 1, those are the group of people that get the drugs. We're going to say that they have higher, and that will be greater anxiety than population number 2. Okay, so they have greater anxiety than population number 2, who are the people that are getting the cognitive behavioral therapy. That's our guess for step number 1. Now we're going to have to move on to step number 2, and in step number 2, we're going to have to take into account those population parameters to make an estimate for our group to make a comparison distribution, because step number 2, as you know, is determine the characteristics of the comparison distribution. We'll do that next. I gotta erase this. Before we do step 2, which is determine the characteristics of the comparison distribution, I need to talk to you about a very serious issue these days. Bias. Bias is rampant, especially if we use t-tests. You're biased in estimating the population parameters that you're going to be using for your comparison distribution. Gossett faced this problem, and he had to figure out, how do I make, instead of a biased test, how do I make it unbiased? Which is something that we're all considering still to this day in a different way. How do I make an unbiased estimate of the parameters that I'm attempting to compare my sample to? And that's a great question, because you see, here's the problem. If I take a smaller version of something and I attempt to pretend that that's the totality of the thing, I miss the variability that exists in the larger thing. So if I take a sample, it's not the entirety of that population. Think of like a carton of ice cream. So I like Moose Tracks, and I like Cookie Monster from Tillamook. Those are really good ones. And in those, they have like these threads going through them, because there's a variety in the population. There's some caramel and some chocolate and these little ribbons of stuff going through, and nuggets. And then there's also like just plain vanilla ice cream all around that. So if you take just a sample, a small sample of it, you might miss the diversity in the entire population. And if you don't do a good job of sampling, the ice cream that is, you'll miss the diversity that exists in that carton of ice cream. And similar thing happens here when we're just testing with only 15 people. We might miss elements of that bigger population that are important. So from that perspective, we have to figure out a way to make ourselves just as likely to underestimate as to overestimate the population variability. That sounds a little weird, but here's how we do it in math. What we do is we take what's called a degree of freedom. So a degree of freedom is the degrees that are free to vary. If you've calculated a statistic, it's how many of your group is free to vary to make sure that that statistic is still true for the group, but they could be any number. Let me give you this example. If you remember my favorite data set, right? We have our favorite data set, 2, 4, 6, 8, 10. How many of these, we all know that the mean is 6, right? Because 2 plus 4 is 8, or 2 plus 4 is 6, 6 plus 6 is 12, 12 plus 8 is 20, and 20 plus 10 is 30, 30 divided by 5 is 6, so we know that the average is 6. For this to be true, for this statistic that we just calculated to be true, how many of these could be any number that you want? They're free to vary. How many? Could I change 1, 2, 3, 4. There's 5 numbers, right? So how many of them could be any number, and yet that is still true for this group of 5 numbers? How many of them are free to vary? Well, throw out a number for me. This is what I usually do in class, but you guys are sitting there and okay, there's 35 of you. 35. So I put 35. Is it still possible that this is true, that the average of this 5 numbers is 6, if I just put 35? That's larger than the total was in general, but of course you know it could be like negative 15 or 2,707, or negative 2.6 million. I made those numbers up off the top of my head, and they can be any number that we want. But this last number right here, that fifth number, is not free to vary if this is still true, that the mean of this group of 5 numbers is 6. Now, you could calculate what that number would need to be for it to yield the mean of 6. I don't want to do that math right now. But you could add them up and then figure out what would be necessary to get the average of those 5 numbers to be 6. I don't feel like doing that. Do you? No? Okay, but here's the concept. Those numbers could be anything we wanted them to be. 4 out of the 5 numbers are free to vary. So in this group, we have 4 degrees of freedom, not 5, because that fifth one has to be the number that makes this true. That's your primer on degree of freedom and how we calculate the standard deviation for a distribution of means is going to be different now from the z-test to a t-test. And for the t-test, we don't actually know the variability of the population. We don't actually know what it is. We're going to have to use our group and its variability, which I haven't shown you yet, to estimate the population's variability. And when we estimate that, we don't want to be biased. We want to use a degree of freedom so that we are just as likely to overestimate it as underestimate it. So here's the issue. Let's say you're out sailing, you're a sailor, and you're crossing the Pacific Ocean, you're going to Australia or something. You always wanted to see kangaroos. And you have a compass. Now that compass orients you to the cardinal directions. But let's say you have a broken compass or bias compass. Now, if you use that bias compass, it's always going to be off to the west. Okay, let's just say that it doesn't point true north. It points towards the west from north. That would be fine if you knew by how much it was off, but here's the problem. It's always off a random amount to the west. So it could be 1 degree, it could be 90 degrees. It's telling you north is this way, but you might be pointing due west. You're not going to be able to navigate with a broken, biased compass like that. If, however, you knew that that compass was just as likely to be off to the west as it was to the east, again, you don't know by how much you're missing that particular true north measurement. What you could do is something ingenious, and that is increase the amount of measurements you made. So increase your n size, and then what you know is that you're decreasing the chance that you're misreading where true north is. Because if it's an unbiased estimate of the population's variability, the more that we have in our n size, the closer we are to the population that we're going to be comparing it to, and so we will have less and less error involved in making those estimates. The larger our n size, the smaller errors that we will have in statistics. Now, frankly, there are sort of basic numbers. If you have above 30 people, you're probably doing an excellent job. If those 30 people were randomly selected from the population, you're probably doing an excellent job at estimating the population that you're going to be comparing it to. However, we have a smaller one here. So take with a grain of salt that if you have a smaller n size, your results might not be as reliable. Okay, I'm using 15 just because I like smaller numbers when I do hand calculations, and I just made it up off the top of my head, so sue me. All right, here we go. We're going to estimate population. Okay, how do we go about taking our sample's standard deviation, which we see here is 5, and using that to create an estimate for the population's standard deviation? We know that if we just use 5, we'll be using a biased estimate of the population's variability, so we're going to transform that by taking into account how large our sample is, and then also utilizing degrees of freedom as Gossett showed us. So first thing we have to do is to calculate S2, which is the unbiased estimate of variance, the unbiased estimate of variance for our sample. And the way you do that is you're just going to take the sum of squares, which we all know how to do, sum of squares, and we're going to divide it by n minus 1. That's it. It's as simple as that. To make our unbiased estimate, we're just going to take our sample's standard deviation, calculate, how do you get sum of squares when all you have is standard deviation, n size, and mean? Well, back to a little trickery here. We can figure this out because, well, what is this? We know that sum of squares in relationship to variance, we know how to figure that out. So we're going to have to do a little bit of math trickery here, and we'll figure out how to get our standard deviation to make us we're going to take our standard deviation and multiply it by itself to get variance. Now we know that variance, its formula, is equal to sum of squares divided by n. So if I know both n and variance, I can calculate what sum of squares is very easily by multiplying this side by n and multiplying this side by n. So 25 times 15 is going to give us the sum of squares, and we can begin to calculate the unbiased estimate. So let's ask Google again. Okay, Google, what's 15 times 25?
The answer is 375.
Thank you. So 375 is our sum of squares. We calculated that by knowing that the variance for our sample is in relationship to n and ss with this equation. So sum of squares is 375. We're going to divide that by n minus 1, or 15 minus 1, which is 14. Okay, Google, what's 375 divided by 14?
The answer is approximately 26.785714.
All right, 28.79. Now we have S2. Okay, for that, we have to do something else. We now have to take into consideration how large is our sample, because this is for a population of individuals. In order to get S sub m, which is our unbiased estimate for the standard deviation for the distribution of means, we need to get S2 sub m, which is the unbiased estimate of the variance for the distribution of means for groups of that size. Now, in order to get S2 sub m, we're just going to take S2, which we just calculated, and divide that by n. Note, we're not going to divide by n minus 1 again. You only do that once. You only take 1 degree of freedom when we're calculating it. So now what we're going to have is, we just figured out what S2 was. That was like that 28.7 something. We'll divide that by n, which will give us the unbiased estimate for the variance for the distribution of means for groups of that size. And then, what are you doing, Henry?
Having a platform to put the bricks on.
He's working hard out there. My middle guy he's a good worker. You don't want to stay for the stats lecture?
I would.
You want to say hi?
Hello.
There you go. All right, that was Henry for now. Okay, back to us. We're trying to figure out the unbiased estimate for the standard deviation for distribution of means of groups of that size. We have to find out the variance for the distribution of means of groups of that size. So now we're going to take what we know, which is S2, the unbiased estimate for the variance for the groups of individuals, divide by n, which is 15, to get the unbiased estimate for the variance for the groups of 15's distribution of mean. It sounds complicated. It's much easier when we just do the math. Okay, so we know that this is that 28.79. We know that n is 15. So, okay, Google, What's 28.79 divided by 15?
The answer is approximately 1.919333.
1.91933. Okay, Google, what's the square root of 1.919333333?
Square root of 3 is approximately 1.732.
I didn't say that. What's the square root of 1.91? Okay, Google, what's the square root of 1.91?
Square root of 1.91 is approximately 1.382.
Good. So again, how do we get from here to here is we take the square root of that number. And when we do, it tells us that we think groups of 15 on average will differ about 1.38 from the mean of their group. Now, if you remember previous iterations when I'm doing z-tests, you might remember that our standard deviation then was really close to that, like 1.35. Now, why is it 1.38? That 1.38, that little difference is just when we take a sample size instead of knowing the population's mean and standard deviation that we're going to compare it to. So again, we're just adjusting this a little bit given that we don't have the full population. That's where those differences come from. So how do you calculate this? First, we take our standard deviation for our sample, 5. Multiply that by itself to 25. That's our variance. We take variance and we divide variance. Well, we find out what SS is given that variance and n multiplied together equal the sum of squares. We divide sum of squares by the degrees of freedom. In our case, it was 14. We get that number, which gives us S2. We take S2 and divide it by n to give us the unbiased estimate for the variance for the distribution of means, and then we take the square root of that number to get our standard deviation for the distribution of means. Another thing this is called is standard error of the mean. Okay? Standard error of the mean means for groups of 15, we bet that they're going to be off by about that much when they estimate the population's variance that they're drawn from. Kind of cool, I guess. If you like math. I do. I kind of like math. Kind of. All right. You might need to watch this several times because I'm going quickly, and if you have problems, we're going to solve those together, and we're going to keep working on this so that you know how to do that. We've only found S sub m yet. We haven't even done the t-test. But now we know what the parameter is for our population. The average amount groups of 15 differ from the mean of their group is 1.38. So now we have step 2 ready to be completed. So you know step 2 is to determine the characteristics of our comparison distribution. We know that the mu is always going to be the same thing as the mu for this, so we know that's 30. Now the standard deviation for the distribution of means for groups of 15 is now 1.38, and we know that's 30. So now what we can do is figure out, well, what's our t going to be? Our t value, or sometimes called the t obtained statistic, that is equal to the mean minus the mu divided by S sub m. So the mean for our group is 25. The mean for the population, the mu, is 30. And our standard deviation for distribution of means is 1.38. So, okay, Google, what's negative 5 divided by 1.38?
The answer is approximately minus 3.623188.
All right, so we got a t obtained, or a t value of negative 3.623. What does that mean? Well, we're gonna have to figure it out. All right, oh, I can't see me, I'm in all dark there. So what does that mean? The t obtained value, or our t value, is negative 3.623. Well, what do we do with that knowledge? Okay, so we did step 2. We determined the characteristics of the comparison distribution. Even when we went advanced, right, and we figured out what the t value is, what do we do with it? Step 3 is to determine the cutoff sample score on the comparison distribution at which the null hypothesis should be rejected. So that'll be next. All right, we're back. We have these things listed down here, our t obtained value, which is negative 3.623. Now we're going to do step 3, and step 3 is to determine the cutoff sample score on the comparison distribution at which the null hypothesis should be rejected. Okay, is this a one or a two-tailed test? Now, I've said that cognitive behavioral therapy will make people less anxious than giving them drugs. So that means that's a directional hypothesis. Less means in a particular direction. Instead of saying, I think that cognitive behavioral therapy will do a different treatment effect or outcomes, that would be a two-tailed test. But I've said one-tail. So this is a one-tailed test. And the alpha level we use, we'll stick with the 0.05 for now just because it's simple. You know what? Let's give you experience with 0.01. Let's do it. 0.01, the alpha level is equal to 0.01. What is an alpha level of 0.01? That means that if we reject the null hypothesis at this level, which is a very stringent level, that means that the chance we're wrong in saying that there's a difference is only 1%. So again, alpha level is the probability that you make a type 1 error. And the type 1 error is saying that there's a difference between, what in our case, cognitive behavioral therapy and psychopharmacology for anxiety. If we say there's a difference at the end, that means that we'll only be wrong 1% of the time if we make decisions about math that way. So I'm very confident if, again, this is all made up. But if this was a real study and we had an alpha level of 0.01, the chance that we're wrong is only 1% of the time. So out of 100 things I say, all of them will be correct except for one. And that's very trustworthy. So this is a very stringent alpha level. And I think we should stick with that for now. If you wanted to do less and do a 0.05, you can follow along with me on this. All you need to do is adjust yourself when we find our t critical value in the back of the book. Now, here's our distribution, our comparison distribution. We know that it had a mean of 30, but now it had a standard deviation for the distribution of means of 1.38. I gotta use my calculator here. All right, so $30 minus 1.38 is 28.62 and 27.24. Okay, so we've got a z-score of -2 would be 27, a z-score of -1 would be 28, a z-score of 0 is 30, a z-score of 1 is 31.38, and a z-score of 2 is 32.76. So we got these numbers, and when we look at them, we go, well, where would we reject the null hypothesis and say that our cognitive behavioral therapy would work to reduce anxiety more than our particular form of psychopharmacology that you get at your local urgent care facility for anxiety or whatever? Well, we've said that it's going to be a 0.01 and it's a one-tailed test. That means that it's in the lower section and it's only 1% of the time. So it's going to be somewhere past here. It's going to be somewhere lower than 2 standard deviations below the mean, because we know that 2 standard deviations below the mean, there's 2%. So we have to go even more stringent than that. So if we look up in the back of the book where our critical value is for a 0.01 alpha level, you're going to have to now use a different part of the book. This is called the t distribution. So here on, this is page 675 in the 6th edition, you see that there's a one-tail and a two-tail test. We're going to stick with the one-tail, and we're going to move to the 0.01 column. It also says degrees of freedom. For us, there was 15 people, so 15 is n minus 1 for degree of freedom. We go down here and we find that our cutoff is 2.625. 2.625 means that the t critical value for us is a negative 2.625. These are all t-scores because we've estimated population variance. They look just like z-scores, but this is actually a t-distribution because we don't have the population's standard deviation. It's unknown. We've used our standard deviation to estimate the populations that we're going to compare it to, and so this becomes a separate distribution. This is Gossett's real true genius, is creating the t-tables that we'll use to find our score, our critical value of a negative 2.625. If we get to that point, if we get to down here, if our score is down there or even lower, then we're going to reject the null hypothesis, right? This is the area for rejection of the null hypothesis. Sorry, I've crammed it up a little bit here on the board. Let's move on to step 4. Step 4. Determine your sample score on the comparison distribution. Now, where is our sample score? If you notice, 30 and 28 and 27, those are the raw scores. Our raw score, our mean was 25. That's way down here, 25. Also, we calculated that t obtained. Remember that t obtained was a negative 3.623? That's way down here. So clearly, we are in the area for step 5, reject HO. So we're going to reject the HO. What do we now do as step number 6? We have to explain it to an 8th grader. Who do we explain this to? We explain it to an 8th grader. Why? Because they don't know about Z versus T distributions. They don't know about standard deviation for the distribution of means. They don't know about one-tailed, two-tailed alpha levels, type 1 errors, etc. But they can know this. Based on our data, comma, CBT, or cognitive behavioral therapy, lowers anxiety better than drugs. See how simple that statement is? Simple, easy, digestible, people can understand it. So we're going to stick with this and say 8th graders could understand that. Now, we've done a ton of complex math here, thanks to William Gossett. Got to give him props. We've used the 6 steps of hypothesis testing, and you're probably still confused. It's okay. This is just our first iteration. We'll do more practice problems as we go. We'll do the homeworks. We're going to figure out what part of this process you don't understand, and we're going to help you to understand it. This is a knowable and doable process. If I can do this, I'm not some sort of a math genius. I've just looked through this stuff a bunch, and we'll go back and we'll find where your error is, and then you don't make that error again, and then you simplify it. It's only a couple things. So please stick with this. I know it's confusing. Watch this video several times, and you're going to get more and more comfortable with the terminology, and then with the steps, when I say we do something, you'll understand what's happening next. Peace out. Okay, class, we're back, and we're going to do another example of a student's t-test. So I pretty normal growing up. Everything was great for me, but I did have this one thing that really sucked. I have giant feet. I have size 15 shoe, and so I could never buy shoes. And my parents were always, sorry mom and dad, throw you under the bus, but they would always give me like one pair of shoe because they said every time they bought it, I grew out of it in like a couple seconds. Now, I have this thing for shoes now, and so I like to buy shoes. I have shoes over there in my garage. I have shoes hanging out there. I have shoes up in my closet. I have shoes under the stairs. I got all these shoes everywhere. But the thing is, that's just me, anecdotally. That's not real. In fact, the story goes that women have more shoes than men, right? That's the idea. But do we know that's true? Well, I do know that the average American woman, according to ShopSmart.com, has 19 pairs of shoes. The article doesn't tell us what the difference was in terms of the variability, right? So we don't know what the population looks like. But I think we can work with this because I just so happened to test the last 15 guys that came, last 25 guys that came through my house, and I asked them, how many pairs of shoes do you have? So the last 25 guys that came through my house and came by to visit, I just said, hey, how many pairs of shoes do you have? And so the average for the 25 guys, the last 25 guys I saw here, they have a mean of 15 pairs of shoes with a standard deviation of 2. Okay. Now the standard deviation of 2, 15 pairs of shoes, we're going to use those numbers to estimate what the population looks like for females. We're going to compare males to females and say, is that old adage true that girls have more shoes than boys, or males have less shoes than females? Let's figure it out. Again, I made all of this data up. Don't take any of this and be like, I learned in statistics class today that the average woman has this. I made it all up today. So please just don't take anything I'm saying here other than I'm trying to teach you how to do a student's t-test. All right, next thing we're going to do is step 1. Population 1, we'll say, is males. Population 2, we'll say, is female. The HO, which is our null hypothesis, is always that there's not a difference between the two. So pop 1 is equal to pop 2. And the HA, our research hypothesis, is that we think, we don't know. We're not sure who has more shoes. So we're going to do a two-tailed test this time. I'll give you an example of that. We don't know if pop 1 or pop 2 are different. So if we don't know if they're different, we do this. Population 1 is not equal to population 2, right? That could be not equal on the low end or not equal on the high end. We're not sure who has more shoes, and so we're going to use this more broad brush for research, and we're going to see if either they have more or less. And I'll show you how to do a t-test in a two-tail non-directional hypothesis. Okay, so step 2. We've done step 1, right? We identified the population, we set our research and our null hypothesis. Step 2 is to determine the characteristics of our comparison distribution. We know that the mu for the distribution of means is going to be the same thing as the mu for the distribution of individual scores, so that'll be 19. I should draw this in pink. 19. What we don't know is the standard deviation for the distribution of means, S sub m. So now we have to go about finding S sub m. We know that the standard deviation for the group of individuals that we tested, that was 2. So what we do is we double that, we square that. So 2 times 2, because that's standard deviation times standard deviation, that equals standard deviation squared, and that equals 4. Great. So now we have standard deviation is 4, or variance is 4, and we multiply that by 25. That gives us 100. So our sum of squares is 100. If you remember how we did this in the last example problem, sum of squares divided by n equals variance. So since we know n and we know variance, we can just multiply variance times n, and that gives us the sum of squares. Sum of squares is 100. I did it so it's nice and easy. These are nice, easy numbers. Now that we have sum of squares, we can say, well, this is a sample, this is not a population, and for us to estimate the population's variance based on our sample, we're going to take a degree of freedom when we estimate the variance of the population. So to find S sub m, we need to find S2 sub m. Now, how do we find S2 sub m? S2 sub m is equal to S2 divided by n. How do we find S2? S2 is equal to sum of squares divided by n minus 1. Another way to write that is degrees of freedom, divided by the degrees of freedom. So that's the same thing. It's just you can write n minus 1 or df, which is the abbreviation that I have here for degrees of freedom. It's the same thing. Okay. I know my sum of squares is 100, so I'm going to take sum of squares divided by degrees of freedom, which is 100 divided by 24. All right, let's do this. $100 divided by 24 is 4.1, basically 7. 4.1, let's just say 7. This is our S2, or our unbiased estimate of the population variance for individuals, not for the distribution of means. To get S2 sub m, we're going to have to divide that by 25. So when we divide that by 25, because S2 divided by n equals S2 sub m, so we'll take S2, 4.17, divide that by 25, which is our n, and that gives us 0.16, extending for forever. Okay, when we take the square root of 0.16, this will give us S sub m, because this is S2 sub m, so if we take its square root, it'll give us S sub m. So, square root of 0.16666666, extending for forever, we get 0.408. Hey, that's area code for San Jose. So we now have our S sub m. We know what we're going to compare our group to is a population that has a mean of 19 and a standard deviation for a distribution of means of 0.48. Now you might want to ask, well, why, if the individuals had a 2 for their standard deviation, is it a 0.408 for that population, for our comparison population? And that's because we're comparing not a population of individuals, but a population of groups of 25 from that population of individuals, so the variability is reduced dramatically. If we were to draw it out, we'll have 19 will be the average, but then it'll be 19.0 or 0.408, or it will be 18.502. I think that's right. No, that's not right. $18.592. That's right. All right, very good. And 18.184. This will be 19.816. So what I've done now is I've taken the standard deviation for groups of 25, the standard deviation for distribution of means of groups of 25, and we've applied it to this new comparison population. Our characteristics of our comparison distribution are that has a mean of 19, standard deviation of 0.408. When we add that to these numbers and subtract it from them, we see the raw scores that groups of 25 will have. So a group of women, you go and you get 19 of them, or I'm sorry, you get 25 of them, and you take the mean number of shoes they have. They're not all going to have 19 shoes, but the average is going to be 95% of the time. The average of those 25 women's shoes will be between 18 and 19. So the average of them, not all the women, right? Some of them are going to have more, some of them are going to have less. But what we're seeing here is when you sample large groups, you're going to get really close to the mean of the population almost all the time, 95% of the time. You're going to get between 18 and 19. When the real average is 19, and we have a 95% confidence that the average is between 18.184 and 19.816. So that gives us a confidence. This is called a confidence interval, or the 95% confidence interval. We'll discuss that more in the future. But currently we're trying to figure out whether or not men or women have more shoes. Okay. Step 3. Well, we need to determine if it's a one or a two-tail test. It's two-tail because we don't know if men or women have more shoes than one another. And we're going to use 0.05 as our alpha level. So for an alpha level of 0.05, two-tail test, what is our T critical value? Our T critical value, we're going to have to go to the back of the book and we're going to look up for 24 degrees of freedom, and it's a two-tail test at a 0.05 alpha level, 24 degrees of freedom. It looks like 2.064. So our T has to be a negative 2.064 or a positive 2.064, just past 2 or just below 2. Now that's where we're going to have to get for our T obtained statistic to be if it's outside of that in this direction, or if it's outside of that in this direction, we'll reject the null hypothesis. If, however, our sample's score is inside of these two, then we're going to fail to reject the null hypothesis. So, step 4. Well, you already know what the mean is for the group of 25. The mean was 15. 15 on this chart is way down here. 15's way down there. So, right now, if you kept this thing going, you get to 15 when you hit Elk Grove. I mean, it's really far out there. What that means is, this represents probably that men don't come from the same population as women in terms of shoe wearing. There's probably some other alternative there's some alternative population out there in terms of the average amount of shoes that men have. So, we can now say we've put our sample score on the comparison distribution, and now we can, in step 5, we can reject the null hypothesis. That the null hypothesis is that population of men and women had the same number of shoes. So we reject that. We reject the HO, and in step 6 we say men and women have different number of shoes on average. Told you I was a little sensitive about it. I went and I counted. I'm the one who has 19 pairs of shoes. I include sandals, by the way, of which I have 5 pairs of sandals. So yeah, I'm a little bit of a shoe dog. Not Phil Knight style, but definitely a shoe dog. All right, so we have men and women have different number of shoes is our 6th step of hypothesis testing. That's explain it to an 8th grader. And you've now seen me go through another entire version of completing a student's t-test. We're going to move on next to t-tests for dependent means. This is a really interesting one because it's a helpful one for us, specifically in psychology, where we're going to have some interventions and we want to measure people before an intervention and after an intervention and find out if those same people were affected by that intervention. So, see you next time.